Sequential color scales are probably the most simple ones. Here we see examples from Color Brewer. The most of the sequential color scales involve one hue only. So really what we perceive here is a change in brightness from light on one side to dark on the other side. This is good because we are perceptually very sensitive to changes in lightness. However, there are also color scales that interpolate between hues, and you can see from these examples that many of these multi-hue color scales are actually employing several hues. So this one starts from a very purple, goes through some blue, cyan, green, to something yellow. So it's not just a direct interpolation in an RGB whatever color space. However, with these multi-hue color scales, we're not just relying on brightness perception. The examples you see are changing in brightness, but there are other examples that do not change in brightness. However, what's more striking is that some colors along such a multi-hue color scale are more light and more prominent than others. So we can see this nicely in the first part. So this right side of the color scale is way more discriminative than these parts on the lower. So we see way more color values on this part of the scale than we can see here. This is even more striking here. This seems all the same dark for me. However, I can see nice steps here in this brightness. Another issue is that I see immediately when the color changes from some green to some yellow here, but here it's all gradually changing. Now, when you want to create these multi-hue color values, don't do interpolations in a color space yourself. Rely on the color values, on the color scales that exist, like these ones from D3, and there are many more tools online that you can find that create you these color scales. Because the ones that are predefined, they usually have some perceptual research behind them. Because the problem is, if you do an interpolation on yourself, it highly depends on how you do this, what sort of color space you use. Now, the upper example in this lower picture is really an interpolation in an RVB color space, whereas the lower one is the same interpolation in a CIE lab color space. So it depends on the parameter space and how you position colors, how eventually you get to an interpolation. Now this brings us to the real problem with color scales, whether these are in fact diverging or sequential, is how do we map our color scale to our data values? Because the simple case, it would just be a linear interpolation. Any step in our data value, we go one step up on our color scale. However, if we compare, as I already said, the lower value on this color scale and the higher values of these color scales, the two red boxes have exactly the same stretch, then we can see that the colors on the higher level of the color scale on the right are more discriminative, more different than the ones on the lower end. So this is where you want to maybe use a different color scaling, not a linear one. So an obvious option is a nonlinear color scaling, where you overemphasize values on the upper level of this scale to the right, which gives us something here where values are more equally distributed, potentially. Of course, it depends how you draw this curve. And the third type of mapping color scales is by discretization. So you could, for example, go stepwise. For every so and so many values on your data axis, you stick to the same value and going on up step by step. So let's look at an example of how these color scaling play out in reality, because there are of course drawbacks for each of these mappings that you use, and when you could use one or the other and when you need to be careful. However, the rule of thumb is start with the simple example, the linear color scale, and then see how does it play out in reality. So let's do that. Let's look at an example. Here we see the unemployment rate for US counties, which ranges from probably 0% somewhere to above 20%, 26% as we can see on our color scale on the top right. Now what we see in this example is this is a linear scaling. So for every 5% we go up, for every values we go up in our data value, we go up one step on our color scale. Now what we see in the graphic is that most of the counties are somewhere in the lower end of the color scale, somewhere around here, really, because they're all bright. What we also can see is that there are these outliers in the southwest. They are somewhere here. So what this linear color scale does, it is overemphasizing the outliers, because the outliers here actually push all the other counties into this kind of color range. So we can't really see any major spatial patterns emerging between these lower countries. At least they're not as prominent as they could be. So one way to do this is to look at the actual distribution of counties. And here we see that most countries are in fact around this part of the color scale. Now one way to do this is to use a non-linear color mapping. And the one that we have here is to look at the median. So the median in statistics, this splits your data set into 50% that are lower than this value, which are these countries, and 50% of the counties in your data set are higher, these ones. Now we map this median to the center of our color scale. It's not anymore here, it's now here. So now what we do is we map 50% of our counties in this part of the color scale and 50% of our counties in this upper scale. Let's do that. What we see now is way better perception of the gradual change here, of these differences between the counties in the middle and the counties here. And we can even see some of these small islands coming up now. So these outliers are now way less disturbing in our data set. Now you could argue, well, can we just remove these outliers to get rid of this problem so we don't have to skew our color scale? Well, if you look at the distribution, if you remove this outlier, it changes not much, because then you have this outlier. And if you remove this one, you need to remove these and these and these and these, and all the way down. The problem is this long tail. And this is quite typical for a lot of data sets, that you have a very, very skewed distribution with a lot of values on one side and then a long leg somewhere else. So between this min and max approach, which is the linear color scaling, and a somewhat skewed one, you can of course push this further. So you can, for example, use quartiles, which then divide your data set not into a lower end and a higher end, but in quartiles where 50% with 25% between each of the ranges. So if we do this, as in this example, we have 75% of our counties lying between this value 1 and 8, which is an 8% increase. So all countries that have between 1 and 8% of unemployment rate are now on this color scale. And the other 25% of our counties have an increase in 18%, right? From 8 to 26% of unemployment. So we can, again, better see spatial patterns. The contrast becomes just more striking. You can even go to deciles, which means that you have 10% of each of your counties or data values in such a bin. So again, we can see very clearly now these counties in the Midwest, in the north of this county, and the sharp differences in the Southwest, which we could barely see here. Once you see them here, you will see them here as well. But it takes way longer to figure out these values here. And there's another advantage if you go for this one, because now you can compare the darkness of this value to somewhere here and say, yes, this is more or less the same. These lines are the same. But this is quite hard to do in something in a graphic like this, where you have to compare values from here to there. However, there's a problem with these deciles, and I'm going to show you this in a second, because work would be too simple. So let's look at these three counties in the color mapping, in the very, very non-linear stepwise color mapping. If we look at the two counties on the right, then we would perceive that their blue values as very, very similar, and the one on the right has a very dissimilar color value. However, if we look at the numbers of the actual unemployment rate, the two ones at the top are actually way closer in terms of the data than the one at the bottom. So using these color scales, nonlinear color scaling, can introduce artifacts in your dataset that you want to be aware of. So as a rule of thumb, start with the linear color scale that is given. If that does not work, if you're not happy, try another one, such as this one, which has more gradual change. It has more intermediate steps. It goes through purple, orange, yellow, and then a bright one. It has way more values, perceptive values that can be perceived as different along this axis as we have along this color scale. So generally, and then you can move to any of the others, but generally try to stay away from them, especially because, not just because the artifacts, but even if you want to explain it, or if you explain it to people, wrapping your head around that this is 10% and again 10% and another 10% might be very, very hard for people to understand.